Hey everyone, welcome to InsightsByRish. In today's video, we are going to implement a project of object detection using YOLO algorithm. And to be more specific, we are going to make use of YOLOv8, which is the version 8 of YOLO algorithm. Now, this is the dataset that we are going to use for this particular project, which is from RoboFlow. I will provide the link of this dataset in the description box. So this particular dataset is from RoboFlow and it consists of images of dogs and cats, which we want to identify. Another point is that we are going to implement this project using Google Colab, and hence we also require Google Drive for this. So we will have our Google Drive here, in which we will be having all our contents. Then we will be having this dataset. Basically, we are going to make use of this dataset, and then the output of this project will be in two types. Firstly, we will try to identify from image. As you can see, this is the original image that we have, and after identifying from this image, we will get these bounding boxes along with the labels of the identified objects along with their accuracy. As you can see, it has identified the image of cat with the accuracy of 92% and the image of dog with the accuracy of 76%. And then another part of this video will be where we will be identifying in real time from the videos. So here I have taken a GIF. As you can see, it's of cat and dog, and after applying the model that we have trained on this particular GIF, we will get this results. As you can see, let me zoom it for you. It will identify the cat and dog from the real-time video. Now this is just a GIF, but actually we are going to make use of a MP4 video. Fine. So this was the output of the project, and we will be implementing it on both the image as well as the real-time video. Now coming back to the dataset part, you can download this dataset in two types. Firstly, either you can download the dataset of cats and dogs depending upon their species. Secondly, you can download the dataset of cats and dogs depending upon their breed. Now for this project, I am going to download the dataset depending upon the species of the cats and dogs and not depending upon the breed. So once you click on this arrow for download, you will get the option in which you want to download this file. So here you can see you have to select a format. So once you click on this arrow, you will have multiple formats here in which you can download this file. You have the Coco, then the Pascal, YOLO and all those stuff. Though we are implementing this project using the YOLO model, still we are going to download this particular dataset in the Pascal VOC format. Fine. So select the Pascal VOC format, and then again we have two options here. Either you can download the zip file of the dataset to your system, or you can just tell them to show the code with the help of which you can download this dataset. I selected the download zip to computer so that this dataset will be downloaded in my system, and after clicking on the continue, it will start the downloading for you. Then whatever files are downloaded to your system, you have to upload them to your Google Drive. Fine. Now before understanding the structure of this project, first let me also tell you that this dataset comes with the annotations. You don't have to explicitly annotate all the images from the dataset. As you can see here, they have shown you that the annotations are already done, which means there are already labels to every object from every image. You don't explicitly have to give labels to them. Fine. So this is one advantage of using the dataset from RoboFlow. Now coming back to the file structure. The structure for this project implementation will look something like this. So first, let's try to understand this. Firstly, we will have a base folder. The base folder will be the folder in which we will be having all our contents, including the dataset and also the Google Colab file and the data.yaml file. Fine. Let's try to understand. So firstly, in this base folder, you will have the dataset folder. Now, in the dataset folder, further you will have two different folders, namely train folder and the test folder. Fine. Then you will have a .ipynb file as well, that is the Google Colab file in which you are going to write the code. That file as well will be placed in the same base folder itself. And then you will have one more file which will be data.yaml that we are manually going to fill, but I will talk about that in the later part of the video. Now coming back to the dataset part, in every train folder, you should have an image and a corresponding XML file to that image and a corresponding text file to that image. So let's say you have n number of images in your training folder. So you should have n number of XML files, that is each XML file for every image, and then also a n number of text files, that is for every image there should be a text file. Now, as we have downloaded this dataset from the RoboFlow, which comes with annotations, here you will be having XML file already present in your dataset. So you will have the image in the JPG format, and for every image it will already have the XML file. XML file is nothing but it holds the information about the annotations of images. And then this text file will not be available from the beginning. Later we have to generate this text files manually. Fine. So we will again talk about that in the later part of the video. But this is how the basic structure of this project will look like. Now coming back to the Google Drive, with the help of which we will be implementing our entire project. I have already created this folder of pets object detection. As you can see in this image, the base folder is nothing but our pets object detection. So once you open this folder, inside that you have one more folder of dataset. As I already told you that in the base folder we will be having our dataset folder. Now further, when you open the dataset folder, here I have uploaded the training folder and the testing folder. These are the dataset that we have downloaded from the RoboFlow. Once you download the dataset in your system, you can further upload it in this dataset folder. Fine. So let me open this train folder for you. Now as you can see, here we are having the image. Along with that, we are also having the XML file for every image. So this XML file is the annotated file for the image. So let me open it for you. So as you can see, this is the structure of XML file. So you will be having various information about the objects present in your image in this XML file. Fine. So let me just close it. Now coming back to the base folder, which is pets object detection. Right now we just have the dataset here. Now next what we have to do. So if you see here, after the dataset folder and the train test folder, next we have to generate a Google Colab file from the same base folder. So we'll come to here and we'll right click, we will click on more, and from this more I will click on Google Colaboratory. So it will redirect us to a Google Colab file. So once the Google Colaboratory file has been opened, you can rename that file. So let me rename it to object detection using YOLO. Version 8, and then click on save. So the file's name will also get updated in the Google Drive, as you can see here. Now you have this Python file in which you are going to write the code for object detection. So this was the second part of the structure. Now the third part of the structure is the data.yaml file. So you will create a YAML file here, and we will try to understand about its significance and what all contents it will hold in the later part of the video when it is required. Right now we will just create the file. Now to create the data.yaml file, we cannot create the file here itself, but we will be creating it using the Google Colab. So let me just open the Google Colab environment. And after opening it, you have to mount this Google Colab file to your Google Drive. To mount that, you will click on this Google Drive icon that you have here and just click on Mount Drive. So the mounting will start, and then you have to just give the permission to connect to the Google Drive. So as you can see, the mounting is successful, and now you have this drive folder in your Google Colab. Open that. In that you have my drive folder. Again open that. In this we have this Colab notebooks folder. In this folder we have created our base directory, that is the pets object detection. You can create this directory anywhere in your my drive, but we have created it in the Colab notebooks. Now once you open this pets object detection folder, as you can see, whatever contents were visible here in your Google Drive, the same thing is also visible here. Dataset and the Python file in which we are writing this code currently. Now this is the base folder pets object detection. Just click on this three dots and say new file. Now name your file as data.yaml, that is YAML, and click enter. So a new file with the title data and the extension YAML will get created in your base directory, which is pets object detection, and the same file will also get created in your drive. So let me just take you to drive, and it will take a moment to update the name and the extension here. So as you can see, this data.yaml file has been created in this drive as well. Now this .ipynb checkpoints will automatically get created. We haven't created this manually. Fine. So this was all about the folder structure. Now we can start with the implementation. So let's go back to the Colab file here, and here we will start implementing the project. So the first part of the project here is loading the data. So let me say here, first is loading the data. So in the first cell, we will start with importing the libraries. So let me say here, importing libraries. And here we will start with importing all the necessary libraries that we require. And we won't import all the libraries at once, but we will actually import it whenever necessary so that we can understand that which library is required when. Now after this cell of importing the libraries, we will have one more cell here of defining the paths. So defining paths. Here we will define the paths to all our necessary folders and files. So let's start with this particular thing first. And for this we will require the OS library. So I will import OS first. So import OS and let's run that. Now we will start defining the paths here. The first path will be the base path. So in this base path, we will have the path to our base directory, which is pets object detection. So let me copy the path from here and paste it here. Fine. So this was the base path. After this, we will have our train path. So train path. Now this train path will be the path to our training folder. As you know, the training folder is present in this dataset folder, and hence we will copy the path from here and paste it here. The next path will be our test path, which will be the path to our testing folder. So we'll again copy the path of test folder from here and paste it here. And the last path will be the YAML path. This will be the path to our data.yaml file. So as you can see, this data.yaml file is present in the base directory. So we'll directly copy its path and paste it here. So this was about defining the paths. Let's run that. So these were the two stages of importing the necessary libraries and defining the paths in loading the data. The second stage of this video is extracting the contents from the XML file, or we can say the information about the objects from the XML file. So let me write here, extracting the object information from XML files. Now what exactly we are going to do here? As I said previously, let me just first tell you what objects are. So if you take a look at this image, here you have two objects in this image. The first one is cat and the second one is dog. So similarly, whatever the use case you are going to implement the model on, you will have n number of objects in your image. Right now in this particular image, we are having two objects, that is a cat and a dog. So these are nothing but the objects. And for every object, we have the information of every object stored in the XML file. So let me just show you. So here we have dataset in our base directory. Let me open that, and from that let me open the training folder. So let me open the first image. As you can see, this image is of cat. Now all the information about this image, or we can say this object, because in this image we are having a single object and that is a cat. We don't have any other object here. So this is a single object of cat, and the information about this object will be stored in its corresponding XML file here. So as you can see, this is the file name, that is, this is the image name that we have here. So inside the file name tag, we have the image name. We don't have to focus on all the tags of the XML file. We just have to focus on the important tags. So after this file name, this is the first important tag that we have. Then we have the size. Inside this size, we have the width and height of the image. So we require these two tags as well. We don't require this depth, but we require the width and the height of the image. So as you can see, the height of the image is 400 and the width of the image is 600. So these are again two other important tags. Then the important tag for us is this object tag. So in this object tag, we will be storing all the information about the object, the name of the objects. As I said previously, we had a single object in that image which was cat, and hence the name, or we can say the label of that object, here it is given as cat. Then we have the bounding box parameters here. Now what are bounding boxes? So if you take the look at this image, you can see there are some boxes around the faces of the objects. Like around the cat as well, we have a box, and around the image of dog also we have a box. So this box is nothing but the bounding box. And when we are annotating the images, we draw similar kind of boxes around the objects. So the values, or we can say the parameters of that bounding boxes for every object are stored here. Fine. So this x minimum, x max, y min and y max, these are all the bounding box parameters in the bounding box tag. So this all the contents we are going to extract of every image. So this is the XML file, or we can say the object information of a single image. Similarly, for all the images we are having this XML files with its information. Fine. So hence we are going to extract this XML information about every object from every image here in the Google Colab. So let's start writing the function here. Let's say def and let the function name be extract object info. In this we will pass the file name. To extract the information now, we require the elementary library. So let's import that. So here I will say import xml.etree.elementary as et. Let's run that. So here first we will create the root. So let me say tree is equal to et, which is an alias given to the elementary module, and here we will say parse. In this parse we will pass the file name which we are taking as an argument in the function. So let me pass that file name here. Then let me say here root, and in this root we will say tree dot get root. So this will be a function, or you can say the method. Fine. Now after making this root, now we will initialize a new list for each file. So let me say here initializing a new list for each file. So let the list name be xml_data, because that list will be holding the information, that is the XML information of all the images. And here we will start extracting the contents. So the first thing that we are going to extract here is the image title. So let me say here extracting image title. By image title, what I exactly mean is, let me open this XML file here. So as you can see, this is the image title that we have with extension, and it is present in the file name tag. So this is the first thing that we are going to extract here. Now for extraction, we are going to make use of this root module, or we can say the root variable. So let's start. Here I will say image title is equal to, we will say root dot find. Now with the help of this find method, we can find the tags, and then we have to extract the information that is present inside the tags. So first we have to find the tag in which we have this image title. So as I said previously, this image title is present inside the file name tag, and hence here I will say file name in single quotes. Let me also make it clear, this file name and this file name that we are taking as an argument here in the function are different. Both are different. This file name is the tag present in the XML file, and this file name that we have here will be the input that we will pass to this function. Fine. And then we are going to extract the text that is present inside the file name tag. So I will say dot text. So this was about extracting the title of the image. The next thing that we want to extract here is the image size. So let me say here extracting image size. So to extract the image size, let me just show you the XML file first. So as I said previously, the image size is present inside the size tag, but we don't require the depth here. We just require the width and height. So to extract the contents, or you can say extracting the value of width and height, first we have to enter the size tag. So let me just say here width comma height. So firstly for width I will say root dot find. As I said, this width is present inside the size tag. So first we have to find the size tag. So here I will say find size. After entering the size tag, now we have to find the width tag. As you can see, this is the width tag present inside the size tag. So now the motto is to find the width tag. Let me say here find width. Now after finding this width tag, the next thing is to extract the text that is present inside this width tag, and here I will say dot text. Fine. And whatever text that we are extracting should be in the integer format. Hence I will just say here int, that is I'm explicitly converting its data type into integer, though right now it's in integer format itself in the XML file, but it might happen that for some images it is in float format, and hence we are explicitly converting it into the integer format here. So this was for the width. The same thing we will again repeat for height as well. So let me say int, and here we will first find the size tag. So root dot find size. inside the size tag we will find the height tag, and after finding that height tag, then we will extract the text. So this was about extracting the image size, that is width and height. Now the third part here is extracting the bounding box parameters and also the name. So let me say here, extracting the label, or we can say extracting the object label and bounding box parameters. Now to extract these parameters, we cannot normally extract this bounding box parameters here. Let me make you understand why. So going back to this drive, as you can see, this is the XML file for the first image. Now as you can see, in this first image we only have a single object, which is a cat, and hence in this XML file for that image we just have a single object tag, because we were having a single object in that image. But let me show you an example where we are having multiple objects in the image. Unfortunately, we don't have any such images in this dataset in which we have more than one object. But let me show you an example of another image. Here we have two different objects in this image. The first one is this person, and the second one is a dog behind that person. So here we are having two different objects in a single image, and hence for the XML file for this image will look something like this. So as you can see, first we are having an object tag for the object person, and secondly we are having one more object tag here for the object dog. So when you are having more than one object in an image, then you will have that many number of object tags in your XML files. So for that, to extract the contents of this object tag, we might need to create a for loop, because we will be having more than one object tag in some of the images. Fine. So going back to this code, here we have to create a for loop so that we can be able to extract multiple objects from a single XML file. So here we will say first objects, and here we will say root dot find all. Now here we are making use of find all because we are finding more than one object in XML file. So hence we are making use of find all method. And what we are going to find? We are going to find the object tag. So let me just open the XML file here. So this is the object tag. So we are first finding this particular tag here. Let me say object. Now after finding this object tag, because we can have multiple object tags, then we will create a loop in which we will be extracting the data from that object tag in a loop. So here I will say for O in objects. First we have to extract the name, or we can say the label of the object. So as you can see here, the label of the object is cat, which is present inside the name tag. So here I will say name is equal to O dot find. What we are finding? We are finding the name tag, and once we find that name tag, then we are extracting the text from that tag. Now we want to extract all the bounding box parameters. So as you can see, these are all the bounding box parameters for this particular object of cat, which are present in the bounding box tag. So first we have to enter this bounding box tag here. So let me just say xmean. The first bounding box parameter is xmean. So here I will say O dot find, and here we are finding the bounding box. So BND box. This tag name should exactly match with the tag name that we have in this XML file, because if this mismatches, then you would probably get error. After finding the bounding box, next you have to find the xmean tag, which is present inside the bounding box tag. So let me again say here dot find xmean. And now once you find this xmean tag, now we are going to extract the text from that tag. So dot text. Again, as I said previously, this should be in the integer format. So let me just say here int. Fine. So this was for the xmean. The same thing we have to repeat for other three parameters as well, that is xmax, ymean, ymax. So let me just copy it, and here we have xmax. Then here we have ymean, and then we have ymax. So xmean, xmax, ymean, ymax. These are the bounding box parameters that we are going to extract. and then we will be appending this all the data inside the XML underscore data list which we created initially, and we will be appending this inside this for loop only, because it might happen that in a single image we are having multiple objects, and for every object we will have a different image title and different width and height. Fine. So here I will say XML underscore data, and I will say dot append. Now in this I will append a list of parameters. So we will create a list here, and in this list first we will append the image title, then we will append this width, then we will append this height, then we will append this name, that is the label of your object, then xmean, xmax, ymean, and ymax. So we are appending a list of arguments here in this XML underscore data inside this for loop only, and then let me come out of this loop here, and here I will return that list. So I will say return XML underscore data. So this was the code with the help of which we are going to extract the object information from the XML file. Let's run that. Now the function is ready. The next task is to call this function and to pass all the XML files in this function. So for that, you are not going to manually pass every XML file one by one in this function, because that would consume a lot of time. So probably what you are going to do is you are going to extract all the XML files from the training as well as from the testing set, and then you are going to pass the bunch of that files to this function. So let's write the code for that here. So first we have to load the XML files. So let me say here, loading the XML files from training and testing set. So here I will create the first list, which is train XML list, that will consist of all the XML files, basically a list of XML files from the training folder. And we'll create similarly one more list, which is text underscore XML underscore list, that will hold the list for all the XML files from the testing folder. Now in this testing folder, to extract this XML files, we will make use of glob module. So to import this glob module, let's go to the initial cell, and here I will say from glob import glob. Let's run that. So let's come back to the list cell, and here we will say glob and also the glob here. Now the easiest way to extract all the XML files from both the training as well as from the testing set is to make use of join method of OS. So here I will say os.path.join. So what we are going to join? We are going to join the train path. As you can see here, we are having this train path, with the help of which we can enter the training folder. So here I will just say train path. And once you enter this train path, let me open that folder for you. So as you open your train folder, in this train folder, you will have some images with the JPG extension and the XML files with the .xml extensions. So once you enter this train folder that you have given the train path here, then you are going to say that you are going to extract all the files from this particular folder that are ending with the extension .xml. So what you will do here, you will join your train path with the extension of files that are ending with .xml. The significance of this asterisk here is that asterisk signifies everything, which means every file that ends with .xml extension. Fine. So you are entering your training folder with the help of this train path, and once you enter that folder, then you are extracting all the files that are ending with the XML extension, that is .xml extension basically. Fine. The same thing you have to again repeat for the testing set as well. Here I will say os.path.join, and here we will pass the test path, which helps us to enter the testing folder. And once you enter that, again you will extract all the files that ends with extension XML. So this was for extracting the XML files from the training as well as from the testing folder. Let's run that. Once you run that, you can even see. So let me just display the first three data from the XML list. So I will say train underscore XML underscore list, and let me display the first three contents here. So as you can see, these are the titles of first three XML files that you have in your train underscore XML underscore list. So you can see this is the first one that ends with XML, this is the second one that is ending with XML, and the last one is the probably the third one. Fine. So now what you will do is you will pass this list of training and testing to the extract object info folder that you created to extract the information from. Fine. So here we will say passing the list of XML files to the extract object info function. Fine. So what you will do here, you will create two new lists here. So the first one is train data. They are the empty list right now. They won't contain anything right now. Later we will append the data in this. And another one is test data. Now you will write two for loops. First for extracting all the information using the training XML list, and second for extracting all the information using the testing XML list. So first we will say for train underscore list. This is probably a variable name. You can name it anything. In map. Now you are mapping what? You are mapping this train XML list onto this extract object info function. Fine. So here I will say extract object info, and here you are mapping this train XML list. So let me just copy it from here and paste it here. So after mapping, then you will append the mapped data to this train underscore data empty list. So here I will say train underscore data dot, and also we are not making use of append method here, but rather we are going to make use of extend method here. So let me say here extend, and we'll pass this train list here. Fine. So this was for the training data. The same thing we are again repeating for the testing data here. So testing data. So here I will say for test underscore list in map, then I will again give the function name, which is extract object info, and then I will pass this test XML list. After mapping it onto the extract object info function, here I will extend it, or we can say I will put that into the testing data list. So here I will say test underscore data, that is this empty list, and then here I will say again extend, and I will pass this test list. Fine. So this is where you are mapping, that is where you are passing this XML list of every folder to your function, and then you are extracting the contents from that, which you are saving in your training data and testing data respectively. Let's run that. This process is also called as parsing of data. So now after running this, we will be having all our training data and the testing data in their list respectively. So let's try to display that. So let me just say train underscore data, and let me see the first three contents that are present in this list. So as you can see, this is the information about every image present in the training data, like the first three images. So this is the image name, then that is the file name, then this is the width, height, then that is the label of the object that is present in the image, then it is xmean, xmax, ymean, and ymax. Fine. So this first list is for the first image. Similarly, this second list is for the second image, and so on. The same goes for testing data as well. Let me again display that. So test data and the first three contents from that. So these are the first three contents, or we can say the first three images from the testing data folder. Now, right now this information is present in the list format. As you can see, this is in the list format. Now we have to convert this information, or we can say this data, in the data frame format. So let me just say here, converting this info in data frame format. Fine. So let's try to build the data frames out of this. The first data frame name will be train underscore df, and the second data frame name will be test underscore df. So here I will say pd dot data frame. Now for this we will require the pandas library. So let me import that first. Here I will say import pandas as PD. Let's run that. So coming back to this cell, here I will say pd.dataframe, and the same thing I will again repeat it for the testing data frame. So here I have to pass this train underscore data list. This particular list I have to pass in the training data frame. And this test underscore data, this list I have to pass in the test underscore df. Now this will hold the data. This data will be converted into the data frame, but we have to give some column names to this data frame, because as you know, the data in the data frame is stored in the row column format. So we require some names to that column, or we can say some titles to that column, and hence we'll give the column names here. So let me just say columns. Here we will give a list of column names. So the first data that we have in every list is the file name. So let me just say file name. The second thing that we have here is the width. So width. The third thing is height. Then after height, then we have the label, or we can say the name of the object, hence name. Then xmean, xmax, ymean, and ymax. This order of the columns in the columns list of data frame exactly matches with the order that we have here. As you can see in this function as well, we have the same order, but just the names are different. Like for the file name, we have given the name as image title and so on. But this list is exactly similar as the list that we are passing here in the columns argument. Fine. The same thing we will again repeat in the testing data frame as well. Let me paste it here. Now let's run that. So now let's try to see some data out our training data frame first. So let me just say here, visualizing train underscore df. First we will try to see the shape of that. So let me just say train underscore df dot shape. So this train underscore data frame consists of 2527 rows and 8 columns. Let me try to display it for you. So train underscore df dot head, and let me just display the first 3 rows. So as you can see here, you have the file name, then you have the width, height, name, that is the label of the object, then the xmean, xmax. These are all the bounding box parameters. Fine. Now let us also check what are the unique labels from this data frame. Now we already know that we have just 2 unique labels, they are cat and dog, but still we will try to check them. Let me say here train underscore df, and here we will pass this name column. Let me just say name, and then we will say unique, with the help of which we can display the unique values from that column. So here we have cat and dog as expected. Now the next thing is, let us try to display the unique file names here, because this file names column right now consists of many duplicate values. Let me also explain you why. As I said, in this image we have 2 different objects in a single image, and due to this 2 different rows will get created for the same image, because for this person 1 row will be created, for this dog 1 row will be created, but only the object parameters like the bounding box parameters, the name will change, but the file name will remain same, because both the objects are present in the single image. File name is nothing but the image title. So this image title will remain same for both the rows, as both the objects are belonging to a single image. Hence we are having many duplicate values here. Fine. And hence let's try to check the unique file names. So let me just say here train underscore tf, then I will pass this file name column here. So file name, then here I will say unique, and I have to check the length of this, and hence I will make use of length method here. So length, let's run that. So this is 2523. So as you can see, initially we had 2527 rows, but after checking the unique data, we are having the 2523 rows. Fine. We can also check the value counts, that is the count of instances for every label. So here I will say train underscore df, then we'll pass the name column, and here I will say value counts. So out of around 2527 rows, we are having more number of instances for dog and less number of instances for cat comparatively. Fine. So this was about visualizing and checking some whereabouts of the training data frame. Now we will also visualize the testing data frame here, because we need to understand the data frames first in order to process further. So here I will say visualizing test_tf. So let's again check the dimension, or we can see the shape of test_tf. So test_tf.shape. This consists of just 358 rows and 8 columns. The columns in the test data frame and train data frame will exactly be the same, just the number of rows, or we can say the instances, will be different. So let me display it for you. So test_tf.head. So as you can see, the columns are exactly similar to what we have seen in the training data frame, and again the unique values from the name column will be same, that is the cat and the dog. After that, we can again check the length of unique file names from the testing data frame. So let me just say here length of test_data frame. I will pass this file name column and I will check for the unique values, basically the length of unique values, which is 350. This means that in our testing data frame, we have no images where we are having more than one object in a single image. That is, in every images of the testing data frame, or we can say the testing folder, we are having every image with only a single object. So this was again the whereabouts of the testing folder. Now, after doing that, this was the second stage of the project, which was about extracting the XML information, or we can say the object information from the XML files. Let's move ahead to the third stage of this video. So let me just say here, the third stage here is calculating the normalized bounding box coordinates and dimensions and label encoding. So in this stage, we are going to perform two things. Firstly, we are going to normalize the bounding box coordinates and its dimensions, and secondly, we are going to perform label encoding here. So let's talk about the first part, which is about normalizing the bounding box coordinates and dimensions. So right now, these are our bounding box parameters, which is xmin, xmax and ymin, ymax. Further, we have to calculate a normalized x, that will be the center of x, and the normalized y, that will be the center of y. And then we have to again calculate the width and height. Fine. And for that, we have some formulas. So let me just show you the formula. As you can see, this is the conversion formula. This center x, this center y, w and h. And these formulas are made from xmin, xmax, ymin, ymax, all the stuff. Fine. We have to implement these formulas and we have to generate new columns consisting of values for this new parameters, which are center x, center y, w and h. This is necessary because these are the normalized parameters without any bias. Fine. So let's go back to the Google Colab here and let's start doing that. So here we will create a for loop in which we can pass both the training and the testing data frame, and we can get the columns, that is the new columns for both of them. So here I will say for df in, we'll create a list here, that is train_df and test_df. Fine. So this new columns will get generated for both the data frames. The first column that we'll be adding in both the data frames is the center x. So center_x. This is the normalized x value of bounding box. Now, if you check the formula here, so the formula is xmin plus xmax divided by 2, and then you again divide the whole equation by width of the image. So let's try to implement it here. So we'll say df xmin plus df xmax. So once you add that, you are going to divide this entire thing with 2. After dividing it with 2, again you are going to divide the entire thing with the width of image. So let me just say here df width, that is this width that we have here in our data frame. Fine. So this was for the center x. Now for the center y, these are the normalized parameters for ymin and ymax. So here I will say center y. Now the formula for center y is ymin plus ymax divided by 2, and here we are dividing the whole equation by the height of the image. So let me just say here df ymin plus df ymax. After adding that, we are dividing the whole thing with 2, and then we are again dividing the whole thing by the height of the image. So here I will say divided by the height, which is nothing but this height column from the data frame. Fine. So this are the normalized x and y parameters. Next we have this w and h here. So let me add the new column here, which is w, and the formula for w is, I think it is x max minus x mean divided by the width of the image. So let me just say here df x max minus df x mean, and we are dividing this whole thing by the width of the image, so df width. Fine. And then we have one more column here, which is df h. In this h, the formula remains mostly same, but the only difference is on the place of x now you have y, so y max minus y mean divided by the height of the image. So let me just say here df y max minus df y mean, and dividing this entire thing by the height of the image. So let me just say a df height. Fine. So these are your new columns that you will be adding in your both training as well as in the testing data frame. Along with that, in this for loop you will be also performing one more thing, and that is label encoding. As you know, right now the labels are in the categorical format, which are cat and dog. We just have these two labels. So let me just say here train underscore df name dot unique. And as you can see, we are having this cat and dog, the two unique values, or we can say these two distinct labels in our data frame. Now they are in the categorical format. We have to convert them into the numerical format because the model and all those functions don't understand the categorical data. Fine. So we are also going to perform it here. Let me just say here label encoding, and we are going to perform it in the same for loop itself. So we will be using the mapping function. First we have to create a dictionary of labels. Let me just say here labels is equal to. Now in this dictionary, the key will be cat, and wherever we find the cat in the data frame, we will replace it with 0. And the second key here will be dog, and wherever we find the dog in the data frame, we will replace it with 1. So this is how we are going to perform the label encoding. We are going to replace the label cat with 0 and the label dog with 1. And then here I will say we will add a new column in the data frame, in both the data frames actually, with the title id, and here I will say df. We are applying these labels. We are applying these labels on the name column from the data frame. Fine. So we'll pass that name column here from the data frame, and here we will say dot map the labels. So this was the for loop. Let's run that. Now after running that, let's again try to see our training and testing data frame here. So let me just say train df dot head. So as you can see, new columns have been added: center x, center y, w, h, and id. id, as you can see, for cat it is 0, and for dog it is 1. The same thing will also be present in the testing data frame, but let me display it here. As you can see, even the testing data frame now has the newly created columns. So this was about the normalizing the bounding box parameters and label encoding the labels. Now we have to move ahead to the fourth stage of this implementation. So let me just say here, fourth stage. This is about creating text files. First, let us try to understand the significance of this text files. As I already shown you here in the structure of the folder, you can see I already told that in every folder for every image, we should have a corresponding text file. Now what this text file will hold? This text file will hold the center x, center y, w, h, and id for every image. That is, for every image, a corresponding text file will be generated, and that text file will hold the center x, center y, w, h, and id value for that particular image. That is because YOLO expects the data in that format, and hence we have to generate them. So let's write a function for that. Let the function name be save underscore labels, and here we will pass the data frame. Firstly the training data frame, and then the testing data frame, and then the folder path. Now here I will say for file name comma group in df.groupby file name. This is because, as I said previously, we might have different files, like different instances with the same file name because of duplication, that is because of having multiple objects in a single image, and hence we are grouping it on file name because we want just a single text file should get generated for every individual file name. That is, for every individual image only a single text file should get generated. But if you don't perform this group by, you will get duplicate text files generated for a single image, and you don't want that. And hence I will group by it on the file name so that for every single image only a single text file will be generated. Now inside this I will say text underscore file name, and here I will say os dot path dot join. Now what are we joining here? We are joining the folder path that we will be receiving here to the os dot path dot split text. I will explain you this just a minute. Then file name and 0. So firstly what is happening is we will pass the folder path. Let's say for the training data the folder path is train path, that is we have here this train path which will help us to enter the train folder. Fine. Once you pass that path here, then what you will do, you will enter that training folder. After entering that training folder, you will split all the titles of the images that you have there. That is, for an image what you have, let me just write the comment here. For every image you have the image title and the extension fine. So you will be having some image title and .jpg extension. So that is, image title is nothing but the file name present on the 0th index, and extension is nothing but the file name present on the 1st index. So what you are doing, you are not extracting the extension of the image files, you are just extracting the image title here, as you can see here, and hence you are making use of split text method here. And after splitting that text of file name, that is splitting the image title and the extension into two different parts and extracting only the data present on the 0th index, that is only the image title without its extension, then you will append, or you can say add a new extension to that, which is .txt, so that the new text files will get generated with the same file names. That is, just the extension of the image file and the text file will be different, but the title of both the things will be same. And after doing that, you will come down and here you will see group. In this group you will create a list, you will pass the ID. Now these are the things or the parameters that we are actually going to store in this file that we are creating here. So what all we are going to store, the first thing that we are going to store here is the ID. ID helps us to identify the class, or we can say the category or the label of the object. So the ID, after that we will have center X, then we will have center Y, then we will have W, and then H. So these are the 5 parameters that we are going to store for every image in its corresponding text file. Then we will convert it to CSV format. So we will pass this text file name here in the toCSV method. Now one thing you again need to be careful about is that this, like though this is a CSV file, but the delimiter shouldn't be the comma. That is, traditionally or typically in any CSV file, the data is separated with the comma. That's what the CSV stands for, comma separated value. But here we don't want the data to be separated with a comma, rather we want it to be separated with a space. And hence I will add a separator here, and the separator is nothing but the space. So that in our text file, the data won't be separated with any comma or anything else, but the data will only be separated with a space. And then here we will say index is equal to false, that is we don't want any index. And also header is equal to false, which means we don't want any header as well. So this is the function. Let's run that function. Right now we haven't created this text files, we have just created the function for it. Now before creating the text files, let me show you the original or the basic structure of the train that we have here. So in this dataset, in the training folder, right now we just have the image in the JPG extension and its corresponding XML file that consists the annotation. Now let's try to add the text files here. So let me call that method of save labels. And in this, I will pass the training data frame. So this train data frame that consists the data for the training folder, I will pass it here. That is this save labels function for the training part. It is taking the df as train df, and the folder path will nothing but the train path. Fine. And the same thing will again repeat for the testing data as well. So here I will call the testing data frame, and instead of train path, we will be passing our test path. Fine. Let's run that. The issue that we are encountering is actually because this 0 shouldn't be present inside the parenthesis, but rather outside the parenthesis. Fine. So let's run that again, and let's run this again. So after the completion of this cell, you can go back to your drive, and now you can see, just a minute, let me refresh this. After refreshing, you can see now for every image, we are not just having the corresponding XML file, but also the corresponding text file. So let me open the text file for you. So as you can see, this XML file is just consisting of the ID, or you can say the label for the first image. So the first image was of cat, and hence the label here is 0. Then the center X parameter, the center Y parameter, then the W, and then the H. So here we have generated such text files for every image, and that every text file will hold the respective parameters for that particular image. As you can see, now for every image we are having the XML file and also the text file. So this was the new addition that we made by using this particular code of creating text files. So that now we are not going to use the XML or JPG files furthermore, but rather we are going to work with the text files. Fine. Now after doing that, the next thing that we want to do here is the 5th stage of the project. So let me just say here 5th stage, and that is creating YAML file. Let's also talk about YAML file. Initially we just created an empty YAML file here in the base directory. Just a minute. As you can see, this is data.yaml. This was an empty file created by us initially in the beginning of the video. Now we have to actually fill some data in that file. So we'll open it from the Google Colab here. Let me just open it. So inside this base folder, we have this data.yaml file. Let me open it. Right now it's empty, as you can see. Now what we are actually going to fill here with? Firstly, we will have the path to our training folder. So train. These keywords that we have here should exactly match with the way I am writing them. You cannot add extra parameters here. So this train will hold the training path. So to copy the training path, let me open the Google Colab environment here. So in the dataset, as you can see, this is the training folder. So let me copy the path of this folder and let me paste it here. And you don't have to put any single quotes here, just paste the plain path. Fine. So this is the path for the training. Next, we have to paste the path of validation folder. Now, as you know, we haven't loaded the validation folder here. We have just loaded the testing folder here, but still the keyword here will remain validation. Fine. Here we will actually put the path of testing folder that we have here. So let me copy that path and let me put it here. Fine. Let me just maximize this. So as you can see, now we are having the training path and the testing path in the data.yaml file, but the keyword here should be validation, not test. Fine. After this, we have to add the next category here, which is NC. NC stands for number of classes, or you can also say it as number of categories. That is the number of unique labels that we have in our dataset. As you know, we just have 2 unique labels, that is cat and dog, and hence the number of classes will be 2. It will depend upon the number of classes you have in your dataset, but in our dataset, in our case, we just have 2 labels, that is a cat and a dog, and hence the number of classes are 2. Then we have to add the list of labels that we actually have. So here I will say names, and in this names we'll create a list. The order of the labels, or you can say the order of the classes, should exactly match with the way they are in the data frame. So let me just scroll up, and as you can see here, this unique values, when you try to print the unique values, they are in this order. Like first we have the label of the cat and then the label of the dog. So this should also be followed here while writing the data.yaml file. You cannot write the dog first. Fine. So the first name that we have here is cat. That is the first label, and the second label that we have here, or the second class that we have here, is dog. Fine. This cat and dog, they should be in the single quotes because they are the string values, or the, you can say, the data of the list. Fine. So this is the data.yaml file, which is consisting the training folder path, the testing folder path, the number of classes that we have, and the labels that we have in our data frame. Fine. Let's save that. After saving that, now we can close it. Now, so this was the stage of building the YAML file. Fine. Once we are done with creating the YAML file, we can move to the next part of the video, or we can say the next stage of the video, which is the sixth stage, and that is about training the YOLO model. So this is the core part of our video, training the YOLO model. Now, to train the YOLO model, first we have to install the Ultralytics library. So here I will say exclamation pip install Ultralytics. Let's run that. Now it will take some time to install the Ultralytics library because our YOLO model is present inside this particular Ultralytics library. So first we need to download it. Now, after importing this library, let me just first clear this output. Before beginning the training of your YOLO model, the first thing that you have to do is to change your current working directory. This is because once you train the YOLO model, it will give you some results in a folder format, and that will get stored in the current working directory, that is the directory in which you are working currently. So if you don't change your current working directory, then all the results that the model gives us, that the YOLO model gives us, will get stored in this Google Colab environment, and you know this environment is temporary. After a while it will get vanished. So it's better to change your current working directory so that the results will be stored permanently. So here I will say os dot, those results are the one that are going to help us in the future for the prediction purpose. Fine. So here I will make use of os, and I will say change directory. I will change my directory to the base directory, that is all the contents or whatever the folder that the model gives us after training will get stored in our base directory of the pets object detection. Fine. So I will just pass the directory here. Let me open it. This is the base directory. I will copy the path of that base directory and I will paste it here. Let's run that. And to confirm that actually this changing of directory has happened or not, you can just make use of ls. That will list you all the contents from your current working directory, and you can see it have listed you the contents of dataset, data.yaml, and the ipynb file that we are currently working in, which means the changing of directory has successfully happened, and right now you are in your base directory. Now you can go ahead with the training of model. Fine. So here I will say from Ultralytics import YOLO. Let's run that. Also, one more thing is that before training of this YOLO model, you have to change your runtime time, because if you continue the execution in your current CPU, it will take you a lot of time, probably 4 to 5 hours, depending upon the number of epochs you give. So it's better to change your runtime type to T4 GPU and then save. Now what will happen once you connect to your T4 GPU? As you can see, the progress has been lost, that is the execution has been restarted. So we don't have to run all these cells again, we just have to run some specific cells because we have already stored all the data in our data.yaml file, so that we don't have to run all these cells again. Fine. After connecting to T4 GPU, as you can see, the cells that you have to run again are the first one of importing the libraries, then the paths, and then you don't require the running of all the cells. Then directly you have to again run the Ultralytics, that is the installation of Ultralytics. And after running this, let me just clear this output again. Again we have to change the directory, and again we'll try to list the contents from the current working directory. Then we'll again import the YOLO module. Fine. And now let's train the module. So here first we'll load the YOLO version 8 to be specific. So I will say model is equal to YOLO, and in this we have to load the version 8. We have to specify whatever you are going to work with. Fine. So we will say YOLO, then for version 8 we will say V8, And now again, every version of the YOLO comes in different sizes. We have the nano size, small, medium, and big. So depending upon whatever size you are going to work with, you have to specify it here. We are not going to work with the nano module because it's very small, and also we are not going to work with the medium module because it's comparatively large for the use case that we are performing right now. So we will go ahead with the small module, which is somewhere between the nano and the medium. Fine. And then we will say .yaml. Now again, this YOLO version 8 comes in two different modes. The first one is this .yaml, where we are building all the contents from the scratch, and the second one is .pt. In that, pt is nothing but the pre-trained model, where you directly import the module and directly make the predictions depending upon the input that you are feeding. You don't have to do all this stuff there. Fine. As we are building everything from scratch, we will go ahead with the YAML way. Let's run that. Now, after loading this module, the next thing is training the module. So let me just say here, training the model. Now to train the model, here we will say model dot train. Then you have to say here data. Data is nothing but your YAML file. So you will just say here data.yaml. Now, as I said previously, you are currently in your base directory, which is pets object detection, and hence you don't have to give the entire path of this data.yaml file, because you are in this directory, and in this directory of pets object detection, you directly get this data.yaml file. Fine. So you are passing that data.yaml file here in the data parameter. The next parameter that we have here is epochs. You have to specify the number of epochs you want to. So let's make it 30, because if you increase it to some substantial high value, then it will probably cost you a lot of time. After that, we have to give the batch. Now batches shouldn't be too large because it affects the or hampers the accuracy of your model, and also it shouldn't be too low because then it will be very slow in nature. So let the batch size be 8. That is, in every batch 8 images will be passed. Then we have name. Name is nothing but the title of the folder with which the data will be stored in your base directory. As I said previously, the process data or whatever results that we are getting from this YOLOv8 model after training will automatically get saved in our drive folder. Now the folder name depends upon what you are giving it here. So let the folder name again be model. So this is the code for training the model. Let's start training now. As you can see, this training has been started. So now it will scan the images from your training folder to confirm that no images are corrupt, because if it incurs or if it come across a single corrupt image, then it will basically stop the training process. So here it is scanning for the corrupt images, and as you can see right now, it have scanned 28 images and it have found 0 corrupt images. So now as you can see, the training process has started, and when it scanned the training folder, out of 2523 images, it didn't found a single corrupt image. And even it scanned the validation folder, that is basically the test folder, and even from the testing folder, out of 358 images, it didn't found even a single corrupt image, and hence it went ahead with the training process. After that, you will also see some data about the optimizers used here. So we are using the Adam optimizer, and this is the learning rate that we are having, and this is the momentum. So this is all the information about the optimizer that we have, and this is the image size that we have, which is 640 for training set and also the 640 for the validation set. Now the training process has started, and as you can see here, we have the number of epochs. Here in this column, it will show you the amount of GPU memory consumed. Then here we will have the box loss, that is the boundary box loss, and here we will have the classification loss and all those stuff. Fine. Then here we are having the size of the image. So this is how the training will happen for all 30 epochs. So now the training process has been completed. As you can see, all the 30 epochs has happened. And after the completion of 30th epoch, you can see that it gives you a path. You can see runs, detect and model. This is the path where all the results are stored. So let me take you there. Just open your drive. So this is the base folder, and as you can see in the base folder of pets object detection, now you have one more folder of runs. This runs folder is automatically created by the trained YOLO model in our system, and this is where all the results are stored. Let us open that first. Inside that, again open the detect folder, and now as you can see, this is the model. This is the name that we gave here during the training process. So whatever name you give here, with that name the model or the folder will get stored. Fine. So once you open that, you can see you will be having a lot of things here. So these are all the results that are stored. So this is the confusion matrix. Let me open it. This is a normalized confusion matrix, you can see. So here you have predicted and here you have true. So the class cat is getting detected with an accuracy of 93%, whereas the class dog is getting detected with an accuracy of 95%. Fine. And we don't have any accuracy for background because we don't have any backgrounds here. So this is the confusion matrix. So you have F1 curve, PR curve, R curve, and a lot of things here. As you can see, this is the F1 confidence curve. So you have all these results here. Let me also open this. These are the final results.png. Here you have multiple graphs of training laws, then the boundary box laws, the classification laws, and all those stuff. So then it also gives you some images, if you can see. Let me open it. So as you can see, this square or this box that you have around the faces of all those is nothing but your boundary box. And if you zoom it, let me zoom it, you can see that around this boundary box it is showing us 0. 0 is nothing but the cat. This is the numerical label encoding that we perform. So 0 means cat. Then for this we have 1, which means it is a dog. Even here we don't have the face, but still it is labeling it as dog, which means just from the body and just from some neck posture, and from that it has detected that the object is nothing but the dog. Fine. Even here the face is very half, the remaining face has been cut, still it is detecting it to be 1. And then this is the cat, this is again a cat, and all those stuff. Fine. So this is for your training data. If you want, you can even see it for the validation. So let me open some of the validation images here. These are all the images automatically stored to your system by the model after the training process. So you can see here for the validation, it actually gives you the categorical label. Here you have dog. Fine. Then here you have cat, then again dog, cat, and all those stuff. Fine. So these are the results, the final results that gets stored in this model folder inside the runs folder of the base directory. Now here you have another important thing, one more important thing. Though all these images are important to us, but still we have one more important thing here, which is weights. So if you open this weights folder, you will get this two files, best.pt and last.pt. These are in the PyTorch format. This best.pt is nothing but our best weights. And now for further inference of image or video, we are going to make use of this best weights. Now going back to the coding part, after this entire training process has happened, it has given us a lot of data. Now we will try to test it. So now let me write here the 7th stage of the model. So the 7th stage of the model is nothing but testing the model on an image. So we are going to test our model on both the image as well as on a video, as I said previously in the beginning of the video. Now right now we are testing it on an image, and the image that we are going to use is this image, and the output should be something like this. So this is the image that we are going to make use of, and let me load that image here in our base directory. So let me go back to the base directory, and this is the folder in which I'm going to put that image. As you can see, that image of cat and dog has been uploaded here. Let me open it for you. So this is the image that we are going to use for testing purpose. Fine. Going back to the code, here we will start testing it. So first we will say here model is equal to, and in this model we have to load the best weights. As I already shown you, the best weights are present in the runs folder. In the my drive we have the collab notebooks, and in that we have the base file, and in that base folder we have a runs folder, and in this runs folder we again have a detect folder. In that detect folder we have the model folder, and in that model folder we have the weight folder, or we can say the weights folder basically. Let me open that folder, and in that weights folder we have two files which are best.pt and last.pt. So best.pt consists the best weights. So let me copy that path here, and here you have to put that path in your YOLO. So this is the YOLO module that you have imported from Ultralytics, and in this you have to pass that path. So basically we are passing our best weights to that model. Let's run that again. After doing that, next thing that we have to do is we have to give an image path here. So let me say image underscore path. Here we will pass the path of image on which we have to test our model. So let's copy the path first. So the image is this cat underscore dog.png. Let me copy that path and let me paste it here. Fine. This was the image path. Now we will read the image in the image variable. So this is the image. So let me say CV2. Now we will make use of CV2 module for reading the image and further image related tasks. So let me import that first. So here I will say import CV2. Let's run that. Now going back to the testing cell, here I will say cv2.imRead, and in that imRead method I will pass this image path so that it will be able to read the image after going to that path. And now we will make our model predict from that image. So here I will say results, and here I will say model. Now this model is this variable in which we have loaded our best weights. Fine. And here I will say model.predict, and in this predict I will say source. So you have to pass the source of image is equal to image path. So here we will pass this path of image with the help of which it can view that image. So let's run that. So as you can see, the prediction process has happened. After that, now we have to display the image with its detected labels. But as I already shown you here, we also have to draw the boundary box around the figures. So these are the two objects that we have, cat and dog, but we also have to label them. That as you can see, the cat and dog are the labels to them, along with the accuracy with which they are getting detected, and also the bounding box around them. So now we have to write a function to draw this bounding box and to give these labels with their accuracy. So let's say here function to draw bounding box with label. Fine. Let's start writing the code for same. So here I will say def, and let the function name be draw bounding box with label. So what all things we have to pass to this function? The first thing will be our image. First we have to pass the image to this. Secondly, we have to pass the label to this. Thirdly, we have to pass the bounding box parameters, that is xmin, xmax, and then the color. Now this color here will be the default argument. That is, if while calling the function, if we don't pass any color, then by default this will be the color, that is 255, 0 and 0. Fine. But if while calling the function, if we give any color there, then this particular color will not be selected. And then we have to give the font. Again, it will be a default parameter. That is, if while calling the function, if we don't give any font, if you don't mention any font there basically, then this is the basic font in which the label will be displayed. So this is nothing but cv2 dot font underscore Hershey and simplex, this one. Fine. So these were the default arguments. Now in this function, first we will say xmin, comma xmax, comma ymean and ymax. These are nothing but the boundary box. Fine. Then we will actually try to draw a rectangle around the object. So we'll say cv2.rectangle, and in this rectangle we will pass our image. Then we will pass this xmin, comma ymean, and then a pair of xmax and ymax. So if you see this image, let me just show you this image. You can see that the corner of the bounding box, to be more specific, the left top corner of the bounding box is your xmin, ymean, and the right bottom corner of the bounding box is your xmax, ymax. Fine. And that is what you are passing it here. Then you will pass the color and the number of labels you have, so 2. After that, you will define the font parameters. So let me say the font parameters. So in this font parameters, you can define different attributes about the font. So let me just start with font scale. Now in this font scale, you can give the font scale anything. I will keep it to 0.8. Then we can give the font thickness here. So font thickness, I will keep it to 1. And after that, I will give the text size. So text size, comma underscore. Here I will say cv2 dot get text size. I will pass the label here, then the font, then the font scale, and then the font thickness. So basically what we are doing here is we are extracting the font size depending upon all these parameters that we have already specified. So depending upon whatever parameters we are specifying here to the font scale, font thickness and all those, depending upon that, the text size will vary. After that, we will position the text within the bounding box. So in this image, if you see, the label, that is the cat and dog along with the accuracy, are perfectly positioned on the rectangle, a small rectangle shown on the top of boundary box. So these labels of cat, dog and with the accuracy, they are positioned on the minimum parameter of the bounding box, that is on the x min, y min. And this is what we want to do now. So coming back to the code. So here we are going to say position the text within the bounding box. So right now we are just positioning the text. So here I will say text x is equal to x min, and then we'll say test y is equal to max of y min minus 5, then the text size at the position 1 plus 5. Now after adjusting this text position, now we will be focusing on the background rectangle there. So let me start here with drawing the text for better visibility. Fine. So the background is a rectangle. So I will again say cv2 dot rectangle. Just a minute. Now in this, I will again pass the image, then the parameter, that is text x that we gave here. Fine. So text underscore x, and then text underscore y minus text size at position 1 minus 5. And then here I will put a comma, and coming down here I will say text underscore x plus text size at 0, comma text underscore y plus 5. And here I will give the color. So color, comma minus 1. After that, we will try to draw the text with the anti-aliasing. So let me just say here, draw the text with anti-aliasing. This function actually consists only about the designing parameters of the boundary box and its labels. Fine. You can give these parameters anything as you want to, whatever color you want, whatever font thickness and font attributes you want, and all those stuff. Fine. Even if you don't give the background rectangle, it's still okay. So here I will say cv2 dot put text. Here I will again pass the image, then the label, then I will again pass this text x and text y, then I will pass the font, then the font scale, then the coordinates 0, 0, 0, and then the font thickness, then the line type. So the line type, let it be cv2. You can again change the line type as you want. I will keep it to cv2 dot line AA. Fine. Actually we have a comma here. Just a minute, let me give that comma. So let's again run it. Fine. Now what we are going to do is, this results actually consist of all the predicted data about our image. Now we are going to loop through these results, and then we are going to apply this bounding box function on that. Fine. So let's say looping through results and drawing bounding box. Fine. So here I will say for result in results and for box in result dot boxes. So basically we are not giving the any parameter explicitly. We will extract the data that the results variable holds after predicting on the image, and that data we are just simply passing it here. So here I will say x mean comma y mean comma x max and y max is equal to map. Now what we are basically mapping is int and then box dot xy at 0, and these are the bounding box coordinates. After that, here I will say label. So label is equal to result, so whatever the predicted labels are, and then I will say names, because names are the variable in which we have the actual labels. As you know, in our data.yaml file we created a list titled as names, and in that we had the labels. So it's result.names and then int box.cls, that is whatever the object label will be, that will be given here. Fine. And after that we will say confidence. In the confidence I will say box dot confidence, that is conf at the position 0. Here we want the label with confidence score. So I will say label underscore with confidence is equal to f, and first here I will pass the label whatever the detected label is, and after that I will pass the confidence score. So confidence, and I want it to be up till only second precision point. Fine. After this, here we will call the bounding box function, that is calling the bounding box function that we built here in this particular cell. So we are calling this function now in that results for loop. So let me call it here, and in this I will pass the image, then the label with confidence, this variable basically, then x mean, y mean and x max, y max, and then the color. Now whatever color you want, you can give their respective RGB values here. I want this particular color that we have here, which is a kind of blue color, so I will keep it accordingly. I will keep it 255, and let's run that. So the issue is text y is not defined. Let me just check once. The issue is somewhere in this function. So where do we have, okay, actually it's text, not test. Let me make it text, and let's run that now. So now it has run successfully. After this, now we will display the image along with that labels. So let me say here, displaying the final image. So here I will say from Google. Here we have to import a module, because basically CV2 has .imshow method with the help of which we can display the image, but that method is not available here while working in Google Colaboratory, so we have to go with another path. So here I will say google.colab.patches, and from this we will import CV2 underscore imshow method. This is specifically for Google Colab. Fine. And here I will call that. So I will say CV2 underscore imshow. Here I will pass the image, then I will pass the weight key, and let's just keep that to 0, and then I will say destroy all windows. So CV2 dot destroy all windows. Fine. Let's call that. So as you can see, now it's detecting the objects from the image. It is detecting cat with an accuracy of 92%, and it is detecting dog with an accuracy of 89%. So this was testing the model on an image. Now let us try to test it on a real-time video. So in my drive, I have uploaded a video of cat and dog. Let me just show it to you. So this is the video that I have, in which we have both the real-time moving objects, and let us try to detect the faces of the cat and dog from this video. So going back to the coding part here, what we are going to say is, let me just write here, this is the 8th stage of our project, which is testing the model on a real-time video. So let's run that. So now, before actually testing it on a video, make sure that you are in your current base directory. So for that, you just say ls. And from this, you can say, now that you are in your base directory, you are good to go further. So just say here YOLO, then detect, and then predict. Now here you have to say model is equal to, you don't have to give any space after that model. And here you have to provide the path to your best weights. Now, as you already know, your best weights are stored in the runs folder, then in detect, then model, and here you have the weights folder, and in your weights you have this best.pt. Fine, just copy the path of that and paste it here. Now that you are already in your base folder, you just require it after runs, because you are already here till the pets object detection. So you don't require the path before that. Let me just delete it. And then after that, you also have to give the source. Then I will say source. Source is the part of your video. So the name of the video is catdog.mp4. Fine. So this is the part to your video, and this video is already present in your base folder, and hence no need to give any previous path. So let's run that. As you can see, the execution has started, and now it will process it frame by frame. So in this entire video, in total we have around 1112 frames, and it will process it accordingly. Here you can also see that in that particular frame, what it is detecting. Like in this particular frame of 1065 out of 1112, it is saying that in that frame we are having one cat and one dog. Fine. So as you can see, the execution has happened, and the predicted results are now stored in the predict folder. So initially in your runs folder, you had the detect folder, and in that you just had the model folder for all the results of your training process. Now you have one more folder here, which is of predict. And this is the path of the video in .avi format, which you have to further give for the object detection from a real-time video. So now what you have to do here, going back to the coding part, here we will come and here we will say exclamation mark ffmpeg, then -I, and then here you have to give the paths to a AVI file. So the AVI file which is stored here, that path you have to supply here. So it's basically runs, then detect, then in that detect you have predict, and in that predict now you have catdog.avi. Fine. After that, here you will just say -vcode c, and then lib x264. And then here you have to give the name with which you want to save the object detected file. So let me just say here pred.mp4, so that after detecting the objects from that video, the video will be stored in this current working directory, which is the base directory with this pred.mp4 name. So mp4 is basically the extension. Let's run that. So after this execution has happened, you can go to your Google Drive and you can see to your base folder here. It will just take some time to get loaded. And now as you can see, now you have this pred.mp4 file. So let me open it for you. So as you can see, now it is detecting the objects in real time. It is detecting for dog, and as soon as the cat will turn her face towards the screen, it will also detect for cat. So as you can see, now it is detecting for both. So this was testing the object detection model that we trained in real time on a video. So that was the video for object detection using YOLO version 8. I will provide all these necessary files on my GitHub, and I will provide the link of the GitHub code in the description box to check that. This is the main code file. Then I have also provided the best weights here so that you don't have to train all the model from the scratch. You can just take this weights file and further you can evaluate it on different images and videos. Then I have also provided with the image that I have used, the video that I have used, and also the YAML file. You can implement it as per your requirement. Fine. So that's it for the video. Thanks for watching.